Hello students, welcome back to the final lecture on Resonant Converters. Till the previous class we had studied on series resonant converters. We had finished that topic. Today let us very briefly see what is a parallel resonant converter, parallel loaded resonant converter, PLR DC to DC converter. Now these parallel loaded resonant converters or PLR converters are similar to the SLR converters in terms of operating with a series resonant LC tank circuit. In other words, they also will use an LC resonant tank circuit. However, the difference is that unlike the SLR converters, the output stage or load appears in parallel with the resonant tank capacitor. In the SLR converter, the output stage was in series with the resonant tank. That is why they were called series loaded resonant converters. Here the output stage will be in parallel with the capacitor of the LC tank, and that is why they are termed as parallel loaded resonant converters. Now what you see here is a PLR DC to DC converter half bridge configuration. And there are three basic differences or three dissimilarities between the PLR and the SLR converters. The first and foremost one is that this PLR converter appears as a voltage source, and hence it is more suitable when you have a number of loads to be fed from the same source. Okay. This your output stage, you can connect the number of output stages across the same capacity. So it is appearing as a voltage source. The second difference is that here there is no short circuit protection unlike the SLR converter. In the SLR converter, the inductor of the resonant tank was in series with the load, so it was providing inherent short circuit protection. Now, in this case, the inductor is not appearing in series with the load, so there is no short circuit protection provided here, which is a drawback. The third difference is that these PLR converters can step up as well as step down the voltage, whereas the SLR converter was only capable of acting as a step down converter, not as a step up converter. Okay. Let us see the circuit now. What we have here is a LC tank. The input of the LC tank is similar to the SLR converter. We have a DC voltage VD that is split into two equal voltages, VD by 2 and VD by 2. There are two switches here, T plus and T minus, and each one has an anti-parallel diode, D plus and D minus. The input to the resonant tank is the voltage across points A and B. This input will depend on which device is conducting from the input side. If T plus or D plus are conducting, then VAB will be equal to plus VD by 2. And if T minus or D minus are conducting, then VAB will be equal to minus VD by 2. So the input to the LC tank will be equal to VD by 2, and it can be positive or negative depending on which devices are conducting. If this inductor current IL is positive, it will flow through T plus. If it is negative, it will flow through T plus. If the inductor current IL is negative, it can flow through T minus, and it is positive. If it is positive, it will flow through D minus. Okay, this is the capacitor of the LC tank, and across the capacitor or in parallel with the capacitor, you have the output stage. There is a diode bridge rectifier that will rectify the capacitor voltage and supply it to the output side. There is the filter inductor LF. Earlier there was no filter inductor in the series loaded resonant converter because this LR was already in series with the load. So we did not require a filter inductor. Now in this case there is a filter inductor as well as a filter capacitor. The output or the load is resistive connected in parallel with the filter capacitor. It can be assumed that this output current is constant if you are switching frequency sufficiently high and the value of this LF is sufficiently large. So it can be assumed that the output current is constant, and we will be assuming that. Figure B gives you the equivalent circuit of figure A. You have the LC tank here, LRCR. The current through LR is IL. The voltage across CR is VC. These are the input points of the LC tank, AB. The voltage across the input points is plus or minus VD by 2, depending on which switches are conducting. And on the output side, you can treat this as a current source. And the value of that current source, which is IB dash P, will be either plus I0 or minus I0, depending on which diodes are conducting. That in turn will depend on what is the polarity of the capacitor voltage. If the capacitor voltage is positive, current will flow in this manner. These two diodes will conduct, and this IB dash P will be equal to plus I0. Whereas if the capacitor voltage is negative, the lower terminal is positive, upper terminal is negative, current will flow in this manner. These two diodes will conduct, and IB dash B will be equal to minus I0. Okay, so this is the equivalent circuit of the PLR DC to DC converter half bridge configuration. In fact, for the full bridge configuration also the equivalent circuit will be same. The working will be same, everything will be same. So in LC tank, in input voltage plus or minus VD by 2, depending on which switches are conducting or which diodes are conducting, and the current source in the output stage, and the value of this current IB dash P will be equal to either plus I0 or minus I0, depends on what is the capacitor voltage polarity. Now this circuit we have already seen. The circuit in figure B we have already seen when we were studying the basics, resonant circuit basics, series resonant circuit with the capacitor parallel load, where we had seen an input voltage VD, inductor LRCR, and an output current source on the output side. These were the equations that I had given you, and these same equations, inductor current is I0 plus IL0 minus I0 cos omega 0 t minus t0 plus VD minus VC0 upon Z0 sin omega 0 t minus t0, and VC of t similarly same. So these same equations can be used. IL0 is was the initial value of the load current. Sorry, IL0 was the initial value of the inductor current, and I0 was the constant value of the load current. So the same equations can be used once again in this circuit. Depending for every stage, initial conditions will change, and the value of VD will change, as we had seen in the SLR converter. The SLR converter we had seen quite in detail, so I'm not going into that much detail here. We'll simply see this in brief. Okay, 3 modes of operation are given in the book. We will see only the discontinuous mode of operation. So what is happening here at this instant, omega 0 t0, switch T plus is being turned on. Okay, at omega 0 t0, the switch T plus is being turned on. Importantly, at this instant, both the inductor current and the capacitor voltage are 0. This will happen in the discontinuous mode of operation, not in the continuous mode of operation. So at this instant, both inductor current and capacitor voltage were 0, and we are turning on the switch T plus. So as soon as we turn on the switch T plus, what happens? The current starts to build up. Now the output current is constant. The output current is constant. So as long as the inductor current is less than the output current will freewheel. As long as the inductor current is less than the output current will freewheel either through this path or through this path. So basically what is happening is we have effectively a short circuit across the capacitor. So that as long as IL is less than I0 and the output current is freewheeling through the diodes, the capacitor is short circuited, so that the capacitor voltage is 0. So during this stage, this is the equivalent circuit for this stage, where we have turned on T plus, inductor current is building up, a part of the current will flow through here, the output current is freewheeling through the diode. Sorry, the current will not flow through the capacitor. The current will come here, and depending on the magnitude of IL, some part will go here and some part will go here. So basically what is happening is the capacitor is short circuited because of the freewheeling action of the diodes. And as a result, the capacitor voltage during this stage is 0. At omega 0 T1, the inductor current exceeds the output current. As soon as it exceeds the output current, this is the equivalent circuit. And now this is similar to what we had seen previously, similar to this circuit. So these two equations can now be used to find the inductor current and capacitor voltage with the initial conditions that IL0 is equal to I0 and VC0 is equal to 0. Okay. So the current will flow through like this. Because of the resonant circuit, the inductor current will become 0 at omega 0 T2. And now it wants to reverse. There is a path for the reversal of current available, that is the diode D+. So after this instant, current will flow through the diode D+. At this instant, the current again becomes 0. And now because T- is not yet turned on, there is no path for the inductor current to flow. So the inductor current remains at 0. The output current now charges the capacitor. So the output current is charging the capacitor in the reverse direction. That is why the capacitor voltage goes on decreasing and it becomes 0. And once the capacitor voltage becomes 0, the output current will then simply freewheel through the diodes. And both inductor current and capacitor voltage will remain at 0 till the instant when you switch on T- and the half cycle will repeat itself. So as you can see, the switching frequency, this is one cycle of the resonant frequency, and this is one cycle of the switching frequency. And there are some blank spaces here, and both the current, inductor current and capacitor voltage are 0. These blank spaces can be controlled to control the magnitude of the output voltage. Because there are some blank spaces here, the switching frequency will be less than half omega 0. So that was the parallel loaded resonant DC to DC converter. I'll stop the resonant converters here. The topic does not end here. Of course, there is a lot of literature available on resonant converters. But as far as your syllabus is concerned, we'll stop resonant converters here, and in the next class, we'll go to the next topic.